Hello, my name is Jeongbeen Yoon at Posttech, South Korea. I will present our work, Optical Flow Domain Adaptation via Target Style Transfer. This work is jointly done with Sanghyun Kim, Suha, Kwak, and Minsu Cho. Optical flow aims to estimate per pixel motion information across 2 consecutive frames, and the estimated flow information is useful for numerous motion-related problems, such as action recognition. While optical flows are widely used in different environments, most previous methods have ignored the issue of a domain gap between train and test environments. The estimators thus suffer from a significant domain difference, such as clean to foggy or rainy weather. This is a critical issue since the existing flow-annotated datasets are limited, and the cost of collecting such a large-scale dataset on a new domain or environment is extremely high. In this presentation, we introduce a generic method for optical flow domain adaptation, which is applicable to arbitrary domains of optical flow estimation. The proposed domain adaptation approach tackles the domain discrepancy issue in optical flow estimation. Our target style transfer module generates a synthetic target feature, which contains the content of the source but the style of the target. The module enables the flow model to be easily adapted to the target domain by utilizing the properties of the synthetic target feature. From now on, I will introduce our proposed method in detail. This figure describes the overview of our method. A base architecture in Figure A is based on FlowNetC. IS1 and IS2 denotes the source image pair, and IT1 and IT2 denotes the target image pair respectively. TSD modules are placed in the early part of the feature extractor E. The module takes both source and target features, thus making the synthetic target feature that follow the target style with the contents of the source. The discriminator D is appended at the last part of the optical flow network G. The other letters C, F, and R sequentially represent the correlation layer, the flow extractor, and the refinement network. Figure B describes an overview of target style transfer module. Our proposed target style transfer module aims to make a synthetic target feature pair that follows the target style, thus allowing the network to be trained using the target style source content with its flow labels. The TSD module takes S and T as input and produces a synthetic target feature H as output. The module is designed to make a synthetic target feature by whitening the source feature, and then injecting the target statistics to the whitened source feature. Next, I will explain how to calculate both global and local statistics used for generating synthetic target features. To obtain global statistics, we simply calculate mean and standard deviation of the source over its spatial dimension. The statistics are then utilized for whitening the source feature. To exploit diverse local styles from the target, we calculate local statistics of the target. The statistics enables the synthetic features to contain richer target styles. Specifically, we compute the local mean and local standard deviation for each position ij using its local window. Then, the calculated statistics are randomly permuted over spatial positions. The random permutation offers implicit data augmentations for synthetic target features, thus encouraging the model to be more robust to the domain discrepancy. The calculated global and local statistics and then utilized for obtaining synthetic target features. The synthetic target features generated by TSC module follow the style of the target but retain the content of the source. To leverage this property, we impose the motion consistency on both the correlation tensor and the predicted flows so that the motion of the source feature pair becomes similar to that of the synthetic target feature pair. In motion consistency loss, MS is the motion information from the source pair and MH is that from the synthetic target pair. To exploit flow adversarial loss, we append a discriminator at the end of the network. The role of the discriminator is to classify the domain of the flow maps. It is trained by the loss LDIS and is only used in the training phase. The flow network G is trained for generating domain-invariant flow maps to fool the discriminator. Since flow annotations are available for the source dataset, supervised training is conducted for the source by EP loss. We also deploy the source annotations for the synthetic pair as the synthetic target pair preserves the identical motion with the source pair. As a result, the overall loss for the flow network G consists of EP loss, motion consistency loss, and flow adversarial loss. I will present several experiments briefly. This table shows average endpoint error results of VKITTI dataset. We set clone as the source domain for all experiments. Target domains are denoted on the second row of the table. In this table, existing methods are incapable of dealing with domain changes. The performance of FlowNet-S and FlowNet-C severely drops, especially when fog and rain are the target domains. The two domains are very different from clone domain as they are both low light weather. When we apply our method, the network outperforms other baselines. Especially, the method shows its efficacy even when the discrepancy between the source and the target is severe. The figure shows the qualitative results of the VKITTI dataset. The domain of the target images are fog, morning, overcast, rain, and sunset from top to bottom. The results indicate that the FlowNet-S fails to get a reliable optical flow map in the target domains, which have a large domain gap with the clone domain. On the other hand, the flow map results of our method show clear improvements. To evaluate the transferability of our model between two datasets, we select three datasets. We choose Flying Things 3D as a source dataset. For target datasets, we choose Sintel and KITTI. We use the official Raft model for our training, which is pre-trained on Flying Things 3D. This table shows that our method successfully adapts to the target dataset. And our method not only can handle the domain difference between the source and the target, but also can deal with the different motion distributions between them. Additionally, KITTI is a real-world dataset. Therefore, this experiment also shows our model's transferability from synthetic to real domain. This figure represents qualitative results of Sintel and KITTI dataset. As shown in the figure, our method is capable of predicting fine flow fields. In the second row, ours successfully catches the movement of a left arm and a left leg of a person compared with Raft. Additionally, in the fourth row, the method clearly detects the movement of a right side man's head. As shown in the bottom row, the result indicates that our method also can deal with occluded objects. This is our summary and thank you for watching.